So last time we started electromagnetic waves, and we did a few topics up here. So that's what we want to continue, and then we'll start with gravitational waves today. But before we do that, I would like to observe a moment of silence, because as you know, Stephen Hawking passed away today. He was a giant in our field. In fact, many of the things in black holes that I mentioned before were really his pioneering insights and pioneering discoveries. So let us just observe a moment of silence. Okay, so let us begin. So last time, I began by saying why it is that the notion of radiation is non-trivial. It needs some notion of asymptotics. Locally, you cannot tell if there is radiation or not. And I gave you an example of the Poynting vector. And I think that will also be your homework problem to work that thing out. That normally one might think that one can use a Poynting vector, flux of Poynting vector, as an indication or as a proof that there are waves or there are no waves. But we saw that even if you just take a standard Coulomb field of a point charge, which is doing nothing, just sitting somewhere, one would not think that there are any electromagnetic waves there. But still, with respect to some observers who are not at rest with respect to the charge, one actually sees that there is a flux of Poynting vector. And however, if you go out to infinity, then in fact there is no, the flux dies, because the volume element, actually the area element, grows only as r squared, whereas the Poynting vector falls like 1 upon r to the 4th. But in the space-time region, not in the asymptotic region, you cannot distinguish between 1 upon r squared and 1 upon r to the 4th. So that's why you need to go to the asymptotic region. Then we did the null tetrads and Newman-Penrose tetrads, because they're very convenient to extract properties of various fields, both electromagnetic, also Yang-Mills. It's just that we don't have time to do Yang-Mills fields, and gravitational fields. And then we saw the peeling properties. Now the key point about the peeling property is just that if you assume that the field is actually smooth at scri, then the Maxwell field is smooth at scri, then peeling just follows. There's nothing, it just has to do with rescaling of the tetrads, the null tetrads, which are null tetrads adapted to the physical metric, vis-a-vis null tetrads which are adapted to the conformity rescale metric, which brings scri at a finite distance. For physical reasons, I restricted myself to the case where the null tetrads are all to the case where the Maxwell fields are all generated by sources of spatially compact support, and I will look only at the retarded fields, and then I gave the argument that these retarded fields are necessarily smooth at scri. But one might say that supposing I was not looking at retarded fields, I was just looking at any old fields, then what would happen? And then the statement is that no, in general you would not have peeling if you don't just consider, if you just allow arbitrary fields. And as Martin asked me at the end of the class, I could just consider a constant electromagnetic field. It satisfies Maxwell's equations in Minkowski space-time, and that of course would not have the property that it is actually nicely behaved at scri, and therefore it would not peel. So what we need is really the fields which are very well behaved at scri. Now historically, what people assumed was not assumed existence of scri, but in the physical space-time, with respect to the physical tetrad, people assume that that phi naught behaves like phi naught naught u theta phi upon r to the upon r cube plus order of 1 upon r to the 4. And if you just look at physical space-time and assume that in fact one of the this tetrad component of the Maxwell field falls like 1 upon r cube, then using the rest of the Maxwell's equation, you can show that the peeling happens. That is to say, then phi 1 will fall like 1 upon r squared, and phi 0 will, and phi 2 will fall like 1 upon r, which is radiation field. So instead of assuming that the field is smooth at scri, we can also just assume something like this, and then the peeling will also follow. But what we chose to assume that the field is smooth on scri because it is directly motivated by what retarded fields do if the sources are of spatially compact support, as we normally have. Okay. And then we did the so this is the peeling property. This is the peeling property of that, and then so this was the assumption. Assume this, then these things also follow. So this is an alternative way of getting at the peeling theorems, and that is how it was done chronologically. And finally, the spin-wetted fields. That's what we saw. It is just a way of keeping track of fields on a two-sphere, and the property of this fields on a two-sphere. Okay. So now we just want to finish that discussion up here, and what we saw was that if I looked at, for example, phi 2. Phi 2, I had to. So that is just given by at AB times MA in bar B. So it has spin weight -1. And similarly, phi 1 hat has spin weight, we saw last time, 0. And phi 0 hat has spin weight 1. And now what we can do is we can write down the Maxwell's equations, which are on this field f hat AB. So we just have Maxwell's equation, which says the curl of f hat AB 0, and curl of his dual is equal to the source, but near scri. Sources are compact, spatial compact support, so near scri. This will also be 0. So we got homogeneous equations near scri. We're just looking at what happened, the structure near scri up here. And so we can just take these equations. This doesn't matter which derivative operator I choose. So I might as well use the graph hat, which is well defined everywhere in the completed space-time. And so when I take the limit of these Maxwell's equations, we get you get equations for phi 2, phi 1, and phi 0. So you just take this and contract it with various Newman-Penrose tetrad vectors, right? N and L here, and then L here, and work out the consequences. And the 4 of these equations, they are intrinsic to scri. That is to say, involve only u theta phi derivatives. And 2 equations say how fields evolve off scri. So basically, we got some source up here, as the usual thing, and you got some radiation going out to infinity, and so we got scri plus up here, scri minus down here. We are focusing on scri plus. And the question is really, what is happening at near scri plus up here? So in the neighborhood here of scri plus, we see that there are no sources, and therefore these equations are satisfied. And the 4 of these equations tell you what happens intrinsically within scri plus, within this 3-dimensional slice, and 2 other tell you how actually the evolution, how these fields evolve off scri. And these 4 equations that I'm talking about, 4 real equations, these 4 equations up here, these are just that if I take phi 1 dot, which is to say d by du of phi 1 hat, this one all in the case of the rescaled, the components of the rescaled Maxwell field, which is the same as the unrescaled Maxwell field, but in the rescaled tetrad vectors. This should also be Please get that like this. Okay, so this turns out to be equal to f of phi 2 naught. So as you can see here, phi 2 naught has spin weight -1. F is this angular derivative that we introduced last time. It involves ma, and therefore it has spin weight 1. So this has spin weight +1. This one has spin weight +1. This one has spin weight -1. Therefore, the total quantity has spin weight 0, and phi 1 has spin weight 0. So this equation makes sense. And so that really is one of the equations. And then the second equation. So this is a function of u theta phi, and is u derivative. So the time derivative, the derivative along this direction is given by f of phi 2. So this is the angular derivative in theta phi directions of phi 2. And similarly, you get here phi 1 hat dot. So phi naught hat dot. That is the same as d by du of phi naught naught. So these are fields, just functions of u theta phi. So they are just defined within scri. And so d by du of this 1, 2, and 0, they refer to the various components of the Maxwell field, and not here just says the leading order part, which is just a field on scri. So the up naught just says the leading order part, and 1, 0, and 2 refer to the various tetrad components. Okay, so and then this is just equal to f dot. So this is remarkable because what it says is that there is no equation on phi 2. So there is no equation which tells you about how the time derivative of phi 2 behaves. So phi 2 naught is completely freely specifiable. And we know that phi 2 naught is the coefficient of phi 2, of Maxwell field, which falls like 1 upon r in the physical space-time. And so the statement is that this is actually something that is actually we don't put hats on the phi 2 naught side just by convention. So let me not put hats up here. Let me not put hat here. Let me not put hat. So the leading order term I will not put hat, but the field itself I will put hat. Here there are no hats because these are all in the physical space-time. These were in the conformably scale space-time. So phi 2 naught is a freely specifiable. There are no conditions on it. But phi 1 naught, we see here that phi 1 naught, its dot, d by du of phi 1 naught, is completely determined by angular derivative of phi 2 naught. So this is determined by the initial value and whatever you choose for phi 2 naught, right? Because phi 2 naught dot is just given by the angular derivative of phi 2. Sorry, phi 1 naught dot is given by the angular derivative of phi 2. So therefore, if I know what phi 1 is here on one cross section, then I know it everywhere. So I might as well give the value in the distant past. If I give the value in the distant past, then I know what phi 1 naught is everywhere. So here the freedom in specifying phi 2 is a function of 3 variables, whereas here it's just a function of 2 variables up here. And this is non-zero. This is going to be non-zero in presence of sources. And therefore the statement is that in presence of sources, in general, you will have to actually specify the boundary value, the initial value, or the final value at the end here, or somewhere in between. But typically we give it at the initially at u equal to minus infinity. That's what we give the value up here, and then it is determined. And similarly, phi naught is phi naught is determined. By its initial value and so phi 2 together with the initial value determines phi 1, and phi 1 together with the initial value determines phi naught. So the only real three-dimensional big freedom that we have is this. So this is freely specifiable, plus if I give myself what is phi 1 naught at u equal to minus infinity theta phi, and I give you what is phi naught at u equal to minus infinity theta phi, then I know the field everywhere. So what Newman-Penrose framework did was twofold. The one is that it told us it neatly separated out the components of the Maxwell field which fall off like 1 upon r, like 1 upon r squared, like 1 upon r cubed, and asymptotically, and there are corrections. These are the leading order terms up here. And secondly, it tells you that the freely specifiable thing is precisely the component which is 1 upon r. And this is why this is called, as I told you last time, this is called the radiation field. It has the two true degrees of freedom, the Maxwell field. These are the two radiative degrees of freedom of the Maxwell field. We got then the two ones are just given by the real and imaginary part of FAB. So, or if you like, at phi 2 naught and phi 2 naught bar, right? Both of them, and these are in the language of polarization. Phi 2 naught represents the radiative degrees of freedom with plus polarized circular polarization, or self-dual, if you like, and phi 1 naught bar will represent one with which is anti-self-dual, or as the other helicity in terms of polarization. So this is kind of the structure that we got, and what was nice was that we could read out these radiation fields very easily. Now what I can do is the following. I can say that, okay, that's interesting that I got neat separation at scri between parts which I can think of as being radiation and parts which I can think of as Coulombic. This and this is Coulombic because it's really following like 1 upon r squared. So this part we intuitively think of as being Coulombic part. So you think of phi 2 naught u theta phi as being radiative degrees of freedom, and you think of phi 1 naught u theta phi as being Coulombic degrees of freedom. As you can see, this is arbitrarily specifiable. U dependence is arbitrary. It's up to you. You choose one, and I'll get a Maxwell field. And therefore, this is really a sort of it depends on all three variables. It has these two components up here, and so this is dynamical. It depends on time. Whereas here, it also depends on time, but its dynamics is completely determined by the radiative modes. The dot of phi 1 naught is completely determined by the angular derivatives up here. So here the dynamics is determined by radiative modes. So that's kind of very striking thing that, as you would expect, some Coulombic thing, you think that, if you tell me what is that the initial time, initial value, then I know what it is, and then, of course, it does have time dependence, but that time dependence is not arbitrary. It's completely determined by what the radiation field does. So if you like, in the Coulombic part, the non-trivial information is just specifying the value initially at u equal to minus infinity. And then the statement is that it is as u equal to minus infinity. And then the statement is that phi 1 naught is determined everywhere in space-time. This is the main point. Do you have any questions? Okay. So then the statement is that, well, can we see this physics in more, this is the intuition that we are now derived, and can we use it? So for example, we can calculate fluxes of energy momentum. Carried by electromagnetic waves. And this is really carried out at infinity, at scri. I mean, that's where we are really looking at the flux of this. And the question is, what is that flux of energy momentum up here? And you all know that the flux of energy momentum, if I want to have, for example, I can take a slice, which I call t equal to constant slice. So t equal to constant slice here, let me erase this for a minute, not to confuse the diagram too much. So t equal to constant slices are these. So this will be, say, t equal to t0, say. This will be t equal to t naught, say. This is a slice up here that is given to me. And what I'm doing is, I'm just taking a little patch here. And this patch I'm going to call delta. Little patch up here. So basically, I'm taking a space-like plane, and I'm looking at a ring, right, between radius r and radius r plus delta r, if you like that. That's what I'm doing up here. So I would like to know what is the flux of energy and momentum across this patch up here. So what I do is, I just take the patch out at infinity and see what the flux is going to look like. So I'm just looking at this little patch and go to infinity. I can take the whole surface, that will give me the total energy and angular and momentum across entire scri. But I'm just looking at locally a patch up here. And so this is just going to be given by integral, or in the physical space-time, this is just going to be given by energy integral of stress rate tensor times the Killing vector field times unit normal to this surface up here. Let's call it tau v. The unit normal times p3d, where k is a Killing vector field. It's a translation Killing vector field. And this quantity is a flux of the momentum associated with k. So p mu k mu, or p a k a, if you like. So if k is time translation, this will be energy. If k is a space translation, it will be momentum. And this is a flux in the region delta. So this is a flux of this particular constant quantity across delta. Again, if k were time translation, d by dt, then this will be an energy, and if k was d by dx, d by dy, d by dz, then this will be a free momentum up here. So I get this translation clean field, and we want to look at what is happening up here. Now last time we did explicitly limits of various fields in the physical space-time to scri. And we actually saw that the translation Killing vector field dA, this is the d by dt Killing vector field, the limit to scri was just this vector field which you call n tilde a, which was given by n tilde a, which at scri was just given by at scri with this it's just given by g hat ab. So it's just normal to scri. where omega was chosen to be equal to 1 upon r. So last time we saw that this is the Killing vector field. The Killing vector field actually goes to scri and has that limit. So this vector field is of course just the vector field which is d by dt. Or if you like this dA, which is just equal to d by dt. But I also have the space-like Killing vector fields. So I got here TA, then I got a vector field xa. This is space-like space translation. This is a unit space translation. So this is just given by eta ab, not b of x. Similarly, I got a vector field ya, and I got a vector field za. So these are unit translational Killing vector fields. Right? G, X, Y, Z. The limit of this to scri, as we saw, was just equal to this n tilde a. Now you can take the limit of x to scri because you have got. So what you have to do is to express it, the components. So we want to do it, express the components. In the chart. First, u r theta phi, and then replace r by omega, omega be 1 upon r, and then this chart is perfectly well defined as scri, so the components are going to be well defined as scri, and you'll find answers, and you'll find that x exactly up here just becomes sine theta cos phi times n tilde a limit. So they all become both the time translation, which is time-like here, becomes null, but also a space translation, which is space-like here, in the asymptotic limit becomes null. But the coefficient here is just 1, whereas here the coefficient is angular dependent, and it is equal to just given by n tilde a up here. So they all become proportional to each other. All the translation Killing fields become proportional to each other on scri, and here similarly this just becomes sine theta. So sine theta cos phi, sine theta sine phi times n tilde a. So this becomes just cos theta. So you can recognize this immediately. These are just the first three YLMs. Right? Sine theta cos phi is a component of x, if you like, in the r theta phi coordinate system. So therefore, this is just equal to these three are exactly the first three YLMs. So therefore, in fact, all the Killing vector field Ka, which are translations, they all have limits to scri. They are of the type alpha times Na, n tilde a, where n tilde a is just the normal to scri up here. And this alpha is either 1 or the first three YLMs. So in general, this is going to be a linear combination of the first four YLMs. So Y00 and Y1N. So these are just linear combinations of them. Of course, these are real vector fields, so I have to take a real linear combination of them, and that is what happens to this. Yeah, question?
Yeah, I think I got a little confused. So you're computing the norm of these vector fields at scri using the conformal metric?
I'm not computing the norm of anything, right?
No, you're saying that it's null. So I'm
okay, so if I'm computing so the statement is that at the moment I just told you what this vector field is, and this vector field is proportional to n tilde, and n tilde is null at scri, and of course at scri you can only compute using the metric. So yeah. Anytime you are at scri, obviously you cannot use physical metric because physical metric is divergent there. So anytime you calculate the vector. So the important thing is that these are all vector fields in the physical space-time, but they have perfectly well-defined norms, well-defined limits to scri, and the limits are all null. And of course, when I say null, I just mean null with respect to the rescale metric, because that's the only meaning that we have about null, because it's not a metric. That's scri. The physical metric doesn't exist. Okay. So maybe the question that Sina really had is the following: that in the physical space-time, these were all unit vector fields. The norm of this vector field Ka, Kb in the physical space-time was plus or minus 1, minus 1 for TA and plus 1 for everything else. And therefore, of course, for with respect to eta hat AB, which is equal to omega squared times eta AB. Therefore, eta hat AB, KAB equal to plus or minus omega squared, and therefore at scri omega is equal to 0, and therefore the norms are actually 0. But the norms with respect to the rescale metric are not constants, and they become 0 at scri. Is this clear? Okay. All right. So therefore we got this. We know what the limits of these things are. So we know the limits. This is just the unit time translation, so we know the limits of this also. The unit time translation just go to n tilde A, as we saw several times, n tilde A, just unit time translation just becomes that. What about this d3v? Well, if you take now this d3v and express it in this d3v and express it in this ur theta phi chart up here, then you'll find that this d3v, which is dx dy dz, but right with the spherical coordinates and then u theta phi coordinates, then not very surprisingly perhaps this just becomes du. So we're looking at t equal to constant, so t is equal to u plus r equal to t naught. That is the surface that we're looking at. And on that surface, d3v just becomes du times d2v. And d2v is the spherical cross section, which is r squared sine theta d theta d phi. So this d3v just becomes du d2v. This just becomes n tilde, and this also in the limit just becomes alpha times n tilde. Everything is clear? Exactly. So all I have to do is to calculate what this is. So then just substitute what is stress-rate tensor. So if I substitute for the stress-rate tensor, then we obtain here that the stress-rate tensor for Maxwell field is equal to FBM GMM quarter DAB. This is a stress-rate tensor, and let me write this as FMN times times FPQ times GMP. So this is a physical stress-rate tensor, but that now we know that. So we're calculating the physical stress-rate tensor, but we're just going to substitute in terms of fields which are well behaved at scri in order to evaluate this. Again, what are we doing? But evaluating this, and we're taking the limit of this as we go to scri. Okay. So therefore, this object, its F is just put F hat, that is free of charge, and eta. So this is just going to be equal to F hat n. N. That's eta with upstairs index, so that will be equal to omega squared times eta hat. Right? Because it's upstairs, therefore that's equal to omega squared times that, minus 1/4. And I have here 3 etas, but one of them is down, one of them, and 2 of them are up. So I just get again omega squared times F hat times eta. Just get omega squared, so the whole factor omega squared just comes out. And remember, omega squared is just the same as, so this factor is the same as 1 upon r squared, because omega is just 1 upon r. So that 1 upon r squared is going to cancel with this r squared that we have in the volume element. This is a limit, this is a limit, which is alpha times n tilde A. So you substitute now. So we use this fact, use the fact that tau A goes to n tilde A, and K goes to, is in limit. In other words, we're just evaluating it at various values of r, and we're taking the limit as r goes to infinity, which is the same as as omega goes to 0. So therefore Ka is going to become alpha times n tilde. So we just substitute here, right, and take the limit. So this is an exercise that I'll leave for you, and you'll find that this P dot K, that is I got here, the flux of this quantity through delta is just given by the flux here, this interval, let me call this delta scri now. So this would be delta scri times alpha and phi naught whole square times du d theta d2 d naught, which is just the volume element of unit 2 sphere. That is to say, it is just given by sin theta d theta. Because on scri, the metric, the rescale metric, the conformally rescale metric, the two spheres are just unit 2 spheres. So this is what we get. So we again see that in fact the flux of energy, for example, then alpha equal to 1. So for flux of energy, you will get explicitly the flux of energy through the region, the delta up here is the same as a flux through delta scri. If we take a limit to scri of this, is just given by first limit of scri of just phi to naught whole square du d2 d naught. And for example, the flux of the third component of the momentum would be just given by delta scri times alpha only cos theta times so this is the energy momentum that goes through any little region of scri. Of course, I can make this all of scri, then the integral delta scri will just be replaced by scri, and you'll get this total flux of energy momentum up here. So the energy momentum carried by electromagnetic waves is completely expressible in terms of the radiation field, which is freely specified. The Coulombic part doesn't appear. So this is another kind of nice thing about the Newman-Penrose framework, that it extracts from the 6 components of the Maxwell field the 2 true radiative degrees of freedom, which are dynamical and which are freely specifiable. And furthermore, the flux of energy momentum carried by electromagnetic waves is completely expressible in terms of them. You don't need any other information. Coulombic information, like the one which is in phi 1 naught, or maybe there is phi naught naught, that never enters in the expression for the energy momentum. This is what you might intuitively expect. You might intuitively expect that if the electromagnetic waves are carrying energy here, then that energy should be expressible in terms of the radiative modes. Right? These are the dynamical modes. The Coulombic mode is not a dynamical mode, so you would not expect it to carry energy and momentum heuristically. And actually, this is a more precise statement that it is indeed the case. So this framework enables us to make all these things very, very explicit. Okay, so I think we're done with the Maxwell theory. No, not quite. I just have to say a few things about the Coulombic mode, and then we will be done. So what about the Coulombic mode? So if you look at the electric charge, in the physical space-time, the electric charge is just given by star FAB. On any two sphere, you can do this integral, this two form, and that is the, so this is on any two sphere, surrounding sources. These two spheres should surround the source, and then that is the total charge up here. And this is a simple formula. The reason is because Maxwell theory is abelian, so the field itself does not carry a charge. Right? So therefore, the charge is only the sources. The field does not carry charge. In the non-abelian theories, like Yang-Mills theories, the field itself carries charge, and therefore the total charge will not be given by that. It will depend on which S2 you use, and if you want to really get the total charge, you will have to use S2, the two sphere out at infinity, because there is a field between a finite S2 and a field at infinity, and that field itself is carrying some charge. When it comes to general relativity, the same thing is true. Namely, general relativity, the field itself is its own source, so it carries its mass. Therefore, if I just take a two sphere, I will not get the total mass content or energy content or momentum content. I will have to take the limit to infinity. But this characteristic is just because of non-abelian nature of general relativity. It has nothing to do with not directly related to the fact that general relativity is coordinated in the geometry of space-time. That fact complicates the calculations, but physically it doesn't really change anything else. Okay, so we take this, and now I just leave this an exercise. You take this. So this is to be integrated on the two sphere. So basically you are putting here a volume element of the two sphere, theta and phi, at sufficiently large r so that you enclose sources up here. And then you can take the limit. And because it does not depend on the two sphere that you choose, if I take a two sphere like this, and then I can take the limit to scri of these two sphere anywhere. And then the statement is this charge here is the same as charge here. So I can just evaluate on charge up here. And so this is the same as integral on S2 on scri, one of those S2s on scri, times you will find this to be equal to, sorry, this is this thing equal to 1 upon 4 pi times that thing, and that is 1 upon minus 2 pi times real pi. And d2b naught is a unit two sphere volume element. So these are just components, right? Just plug in the components and take the limit, and you will find that the limit is just given by a real part of phi naught. So this phi 1 naught, as was promised, it does fall like 1 upon r squared, and therefore, as was promised, it looks like a Coulombic degrees of freedom, and indeed, the surface integral of that gives us the total charge. If I take star q, magnetic charge will be given by 1 upon 4 pi times integral of FAB. This is the total magnetic charge that is given to you, and so that will just equals to minus 1 upon 2 times imaginary S2 on scri of imaginary part at phi 1 naught into B naught. But of course, this is 0 if we assume that there is a group. There is a global vector potential. That is to say, if F is equal to dA, where A is globally defined, then this will be just dA, this is a compact surface, so therefore it will be integral of A on the boundary, but the compact surface has no boundary, therefore the answer will be 0. And you can also do the same calculation here. You can take the imaginary part of phi 1 naught, and you can see that in fact, imaginary part of phi 1 naught will be given by the angular derivative of the component of the vector potential. Let me call it phi 1 naught is A minus. So therefore, the A minus is just equal to A minus. Okay. So the statement is that this will be given with the angular derivative. This is the identity, and again, it's an angular derivative. So you're integrating some quantity on a two sphere, and therefore it is identically 0 because it has no boundary. So the statement is that this quantity is identically 0 under normal conditions, but this is the Coulombic charge, and that is where the Coulombic charge actually resides. Now there is a very interesting subtlety about angular momentum, but I think what we'll do is to come back to that later when we do when we have done the subtleties associated with angular momentum, also in the gravitational case. Okay, so this ends the part about the Maxwell theory, electromagnetic waves. Now we can begin gravitational waves. Are there any questions? Yeah.
So you kind of separate out like the two true degrees of freedom of Maxwell field into like phi 0, 2. Does it help you like quantize it in a different
Yes.
way?
So the statement is that you can just, what is in quantum theory, the Fock space is all constructed out of these phi 2 knots, and there are issues which are to do with the infrared issues. These infrared sectors and soft charges. Maybe I should just mention that. It has to do the following thing: that if I look at this real part of phi 1 naught, not the integral, but just the real part of phi 1 naught itself, this is often called charge aspect. So this charge aspect is just a function of the two sphere. It's not a very deep thing. It's just a function of the two sphere up here, and the point is that this real part of phi 1 naught is integral, is the total charge. And this will be the magnetic charge aspect, if you like, up here. And this, what the electric charge measures is just the y00 component of this. Because you're just integrating this, so you're just taking the average of this quantity. But of course, it's a function on the two sphere. And the function on the two sphere is so this is a function of the two sphere up here. So what do we see from here? We see from here that phi 1 naught d by du of phi 1 naught is equal to x of phi 2 naught. So I'm not integrating, I'm just looking at phi 1 naught itself. So I can integrate this with respect to just u, not theta and phi, but just with respect to u. So du times d by du, u going from minus infinity to infinity. So this, of course, is just going to be equal to phi 1 naught. U equal to infinity, minus infinity to u equal to infinity. I'm just integrating this, so therefore that this will be equal to integral of x phi 2 naught u theta phi, and I'm integrating u equal to minus infinity to infinity. So the point is that this is a radiation field, so we do expect it to fall off at the both ends. But the energy, for example, is given by phi naught square du. This energy is finite, so we expect it to fall off at least as 1 upon u, faster than 1 upon u in both ends. But in between, it is arbitrary. And therefore, this integral is not controlled. It is finite, but it's not controlled. It is arbitrary up here. Now, if you do quantization using this, which you can, I'll give the references, then the statement is that you will get a Fock representation. And these are the standard Fock space of photons that we all live with. But it turns out that whereas to qualify as a respectable radiation field, which is emitted by some source, this phi 2 naught just has to fall off at some rate, at the 2 rate. In between, it is completely unconstrained. For this phi 2 naught to define a photon state, it also has to have a finite norm, or one particle norm has to be finite. This has to really brings in h bar explicitly, and this has nothing to do with the classical theory. I mean, classical theory couldn't care less if in fact the Fock space norm of this is actually finite, right? Because I just want to know the energy is finite, momentum is finite, I don't know, whatever physical quantity you calculate is finite. I don't care if the Fock space norm is finite. But if the Fock space norm is to be finite, then in other words, if it is supposed to define one photon Hilbert space, Fock space norm finite. So well-defined vector, one particle Hilbert space, one photon Hilbert space. So that implies that in fact this quantity so this is often called Q of theta phi. I mean, this is a maybe little q. It's not an electric charge. It is just the difference between phi 1 naught at plus infinity and minus infinity. Plus infinity and minus infinity. So this has to be equal to 0 for the Fock space norm. But the statement is that I have perfectly well-defined radiation fields for which this is not 0. That means that in the scattering theory, not all states will be represented by elements of the Fock space. Fock space is not sufficient. And this has to do with the infrared problem. It is infrared because you're going from minus infinity to infinity here, if you like. That. So it is really picking out kind of 0 mode of this field in some appropriate sense, if you went to the momentum space. So if in fact, if it is not finite, then we are led to non-Fock infrared sectors of photons. And these non-Fock sectors, infrared sectors of photons, are essential for consistency of the theory if you want to make the S matrix well defined. The S matrix you would like to be well defined between past infinity and the future infinity. And even after your done renormalization to take care of the ultraviolet problem, you ask the question, order by order, is the S matrix well defined on the Fock space? And the answer to that is no. And to cure this problem, what you do is to enlarge your space of states by allowing these infrared sectors. So this Q is often called the soft charge. And there are various theorems in perturbative QED, for example, due to Weinberg, which govern the properties of the soft charge. But most of the content of those theorems can be read off just using the scri framework about properties of what the radiation field does on scri. So the answer to your question is yes. Not only is it true that you can do standard quantization of the photons using these freely specifiable two particle modes, but in fact this naturally tells you that there are infrared issues, and those infrared issues are not taken care of. We're going to see just in the next lecture that, maybe not, in the next few lectures we're going to see that in a gravitational case, these infrared issues are critical. This is what causes the enlargement of the symmetry group from Poincaré group to the BMS group, which we are all going to see. So therefore it's good that you ask the question, that we sort of see a glimpse of it. And I know that this is too fast. You cannot, I don't expect you to completely understand what I'm telling you, but I hope you get a general feel that there are issues which are to do with infrared behavior. And the nice thing is that the Newman-Penrose framework, or to me, just the scri framework, you don't need Newman-Penrose framework for this. The scri framework enables you to look at, provide clear geometrical interpretation for the infrared issues in space-time language without having to go to the moment of space. Yeah.
Just a follow-up question. The way you were just describing it in terms of the Fock norm, it made it sound like it's an anomaly in the sense that it shows up only in the quantum theory. Is that correct?
Yes, but I would call it anomaly in the sense that the concept itself doesn't exist. I mean, anomaly is usually used for terms that there's a conservation law, which is right-hand side is 0, and it is not equal to 0 in quantum theory, but it's 0 in the classical theory. Here, I'm just calculating the Fock norm, and the statement is that there are perfectly reasonable configurations of the radiation field for which a Fock norm is infinite. So Fock space just does not handle them. Those are not photon states. Then the question is, but I can produce them. So how am I going to represent them? And the statement is that you have to enlarge the Fock space, standard Fock space freedom, standard Fock space framework to allow for these kinds of fields.
So two comments. I mean, you can cast this as a conservation law, can't you? I mean, in a sense, it's conservation of the soft charge along scri.
It's not conservation, right? It's just total. This is a definition of soft charge. Soft charge is not defined. I mean, it's phi1, phi2 this is an integral, right?
I guess I mean from scri minus to scri plus.
Oh, okay, minus to scri plus. Right. So if you look at it from scri minus to scri plus, then that is exactly the way that the attitude that is taken in the Weinberg soft theorems and so on. That one wants to go from scri minus to scri plus. The treatments. So morally, the answer is yes. It is like that. But in fact, in the treatments, there are all kinds of formal assumptions made, because one is assuming that the S matrix is well defined in the Fock space, and then one arrives at this, but S matrix is not well defined in the Fock space. It's full of kind of not unsatisfactory features, which can be given meaning to and such thing, but that is a big detour.
Okay, yeah, I understand if you don't want to go here either, but the other question I had was about to what degree is this classical? Because the memory effect sort of seems like it's a classical phenomenon.
Yeah, it is a classical phenomenon.
And so...
So this is also memory. So the statement is that if I have some of you might have heard of electromagnetic gravitational electromagnetic memory. We'll do gravitational memory in more detail. The idea up here is that supposing I got some electromagnetic waves which is just going out here. Okay, just going off some electromagnetic waves there. And I have some particle which is going, a charged particle which is actually going in these electromagnetic waves. So the statement is that there is going to be a kick in the velocity between going from here to here, and that is completely measured by this soft charge. So in that sense, it is, you have to sort of distinguish between physical phenomena and mathematical basis of this physical phenomena. So this is a physical phenomena which is just classical, and the mathematical basis is this soft charge up here. The infrared issue is a quantum mechanical issue, but its mathematical origin is again a soft charge. So, but it's a quantum mechanical issue because it has to do with finiteness of the Fock norm, which I cannot ask in the classical theory. And the Fock norm actually, as you might imagine, because it is a norm, so it is dimensionless. It actually involves 1 upon h bar times. So explicitly you see that. It really requires a quantum theory up here. So to what extent is it a classical thing and a quantum theory? It depends on what you mean by that. If by it you mean the soft charge, well, it's a classical thing. But its implications that you have to go outside Fock representation to define, make the S matrix well defined, is quantum mechanical. Yeah, I think the thing from scri minus to scri plus is very interesting, and there are true statements, but there are also statements which are very vague, that are not, it's not necessarily false, but they might be, some of them might be empty. Okay. All right, so this is where we are, and now what we want to do is to begin gravitational waves. So this is a very long, several weeks topic. Not very long, but several weeks topic. And what we want to do up here is really return now to what we mean by asymptotically flat spacetimes. I just want to recall our various notions, because that is what we are going to use in gravitational waves. This whole detour to the whole discussion of Maxwell fields was to introduce you to techniques that we are going to use in a more familiar context. Of course, you are not familiar to phi 2 naught, phi 1 naught, etc. But you are familiar to FAB, you are familiar with the special tensor, you are familiar with the electric charge, you are familiar with the flux of energy. And what we have done is to take those familiar notions and cast them in a language which actually is going to go over also to gravitational theory. So here, in the first part of the electromagnetic theory, we saw that it is tricky to talk about the radiation. And therefore, we saw that scri provides a natural arena to define radiation, basically because we are going to R equal to infinity along null directions, and that is, so to say, roughly following radiation. There's also backscattering. But the principal part, if you ignore the backscattering, is going along null directions. So that's what we did for asymptotically flat spacetime. So let me recall for you, because we're going to use all these notions very, very critically up here. We're given a spacetime. Now I have to do a change of notation. I hesitated a great deal about it. But now we're going to talk mostly about the conformally completed spacetime. All the radiation and everything is going to be conformally completed spacetime. As we're seeing here already, everything was in the conformally completed spacetime. These equations are all in the conformally completed spacetime. So instead of putting hat on the conformally completed spacetime, I'm going to put hat on the physical spacetime, which I hope doesn't confuse you. But from now on, I will follow it uniformly, that hat is always on the conformally completed spacetime. So now we change our notation. Otherwise, I think every formula has hats, and that sort of is totally redundant. So that's what we're going to do. So we're going to talk about a physical spacetime now, which is given to us. And we'll be interested in physical spacetimes M hat G hat AB, which satisfies Einstein's equations. The metric satisfies Einstein's equations, so it is equal to 8 pi times G Newton times T hat AB, such that satisfies Einstein's equation. That's what we will go to. And now we are going to assume the space-time is said to be asymptotically flat if it satisfies the following condition. There exists a space-time now MGMB, conformally completed, where M is M hat, union is boundary scri. Scri is topologically S2 cross R, and GAB is equal to omega squared times G hat AB, with omega equal to 0, and I'm using the notation we already introduced. Hat just means equality holds at scri, omega equal to 0, and grad A of omega is not equal to 0 at scri. So that is to say, we're just saying that omega is a good coordinate. In scri, and omega equal to 0 and grad omega is equal to 0. This heuristically, this is completely heuristic, but it's a very useful intuition. Heuristically, it just means that omega falls like 1 upon R. It's heuristic because I don't know what R means, right? Because a priori, given Kurt's spacetime, I don't know what R means. But if it was like a Minkowski spacetime, then it is like 1 upon R. Yeah.
Yeah, I've always wondered how essential is the assumption of the topology of scri. I mean, so for instance, if the topology were R3, could you still define a similar notion of asymptotically?
Yeah, you can. It's similar, but it's not the same. So the statement is that the group will not be the BMS group. The universal structure will not be the same. There will be the wild tensor doesn't have to vanish at scri.
Oh, it doesn't. If it's
So there are several things which are completely different if you don't have strict topology. But you can do it. I mean, there's nothing. You can classify it into compact topology and non-compact topology. The question is, why are we doing this? I mean, if you're a mathematician, of course, there's good reason to do it. But if you're a physicist, I mean, this light cone up here is really, this S2 here is coming out of the light fronts. And the light fronts far away should look like two spheres. And so if that is not going to look like two spheres physically, that the motivation for S2 cross R, then I got some source which is emitting light fronts, and this is really the locus of this endpoints of these light fronts, light cones. So if you're saying that, well, no, I don't want light cones to look like that, it's just not physically very interesting.
But can you still define some notion of like gravitational radiation, even if the?
I mean, again, these are vague questions. Right? What do you mean by gravitational radiation? So you have to first tell me what you mean by it, and then I'll tell you whether you can do it or not. I just said the wild tensor is not 0, so you have to say what do you mean by gravitational radiation first, and then there's not much literature about this. There's no obstruction in doing that, but it's just completely poorly motivated. So. Two. Physical spacetime is this, if this is true. And these are locally, so we're not asking sky to be global, so we're just asking it to be around locally up here. That's what asymptotically flat means. And the second is, so this is omega is a good coordinate. Yes, and the second is about the conditional stationary tensor. We say that omega to the minus 2 times t hat AB. The physical stationary tensor has a smooth limit to scri. So we're only going to be assuming these properties. So you might have some sources in between. These sources might be binary black holes. They may be a collapsing star, which actually supernova explosion that is actually sending out gravitational waves and so on. So all those things are possible. And then omega minus 2 times t hat AB has smooth limit to scri. So that's what we're assuming, and we motivated this when we're doing black holes. And then the statement is that consequences are. It's a very weak requirement. In particular, we do not require that every null geodesic has an endpoint or scri or anything like that. That is absolutely not necessary for gravitational waves, for theory of gravitational waves. This is what mathematicians often use. They use the notion of asymptotic simplicity due to Rao Penrose. which has which requires that every null geodesic has an endpoint as future endpoint as scri minus and past endpoint as scri plus. Past endpoint as scri minus, and that is very hard to check in practice that space-time satisfies this condition because you will have to integrate every possible null geodesic. And the important thing is that for scri, for gravitational waves theory, it is absolutely not necessary, and it is also not necessary for black holes. So it is a useful, stronger requirement to use, and a lot of theorems actually use that. But I want to emphasize that that assumption is much stronger than what we're using up here. I'm saying it because it's being also recorded, because in the literature you'll see the only asymptotic simplicity very widely used in geometric analysis literature up here. Okay. But consequences of this immediately are where that that in fact that we're going to confound freedom. Yeah, wait just a minute. So we're going to confound freedom, and the confound freedom just corresponds to omega goes to little omega times omega, where little omega is smooth and little omega is not equal to 0 anywhere on scri. It's nowhere vanishing in scri. That's the conformal freedom that we have. And what we saw last time, but several lectures ago when we did asymptotic flatness, was that in fact we can reduce this freedom, and that's very effective to reduce it because then the calculations simplify greatly. So the reduction of this freedom is brought about by noticing that we can use this freedom to go to confound frame. Confound frame just means twice of omega. For which so we just use it to make it scri divergence free. There is one consequence, so that using these field equations, we can check, we can show that we can always do that. And the second thing is that, in fact, using field equations, these field equations and the follow-up property of the stationary tensor, that NA is null. So scri is a null surface. So if I take the, so this implies that if I take the metric GAB, the conformally rescale metric, and pull back to scri, and if I define this to be QAB, this metric is smooth, and it has the signature 0 plus plus, and QAB and B equal to 0. And then the third consequence, which is also non-trivial, which again uses field equations, and the fact that I make this equal to 0, in that conformal frame, it follows that in fact something much stronger is true, that the covariant derivative of n itself vanishes in scri. So this is called the divergence free frame, and the statement is that in any divergence free frame, in a divergence free conformal frame, we have a strong requirement that grad A of NP, the covariant derivative itself vanishes. So this in particular, of course, implies that grad A of NB vanishes. So this in particular implies that this vanishes, and this is just equal to Ln of GAB. And therefore, if I pull back this equation to scri, Ln of GAB equal to 0, I pull back to the scri. This is the kind of thing that we did quite frequently in the analysis of non-expanding horizons. Then this would be equal to 0. But this on the other hand is just Ln of QAB. So we get two properties. One property is that QAB is NAB equal to 0, and the second property is that Ln of QAB equal to 0. So we're always going to work in this conformal frame, and maybe I should just say one more thing because that ends this topic, and then we can start with the new topic next time. And what we mean by asymptotically Minkowskian spacetimes right, is asymptotically Minkowskian. So it's not only asymptotically flat, but it is globally asymptotically flat. And we needed that, for example, to define black holes, because to define the horizon of a black hole, we needed the scri to be complete. So that is to say, scri is complete. So asymptotically Minkowski spacetime is such that MGAB is asymptotically flat. And in a divergence-free conformal frame, which we can always use, and we will use, in this divergence-free conformal frame, NA is a complete vector field. What this just means is that the affine parameter of NA greater U equal to 1. And so this condition is a complete vector field. Just means that if I use the affine parameter, then U is in minus infinity to infinity. Okay, so that's what we had shown before. And one of the consequences I should have written down up here is that if you go to the such conformal freedom, conformal scri to be divergence free, then we have that the restricted freedom now is that the restricted conformal freedom that we got, now omega is allowed to go to little omega times omega, where ln of omega has to be 0. So this omega, little omega, is a function only of theta and phi. So I will summarize next time all this very, very quickly, the structure, that we'll work with asymptotically Minkowski spacetime, in which scri is complete, admits a conformal completion, topology is 2 cross R, and then we know that this is a null surface. The QAB is intrinsic metric, which is degenerate, and it's Lie dragged by n, and this n is complete. So these are the conditions that we'll be using. So that's what we are all set now, and we want to understand. This is this kind of a physically motivated conditions on geometry, and now we go back and say that, well, if these are the conditions of geometry, what does geometry tell us about physics? So we went from physics to geometry here, and now we're going to do the other way around. We're saying, okay, so this is the case, therefore geometry has some properties. What are those properties in terms of physics? That's what we're going to study in the next few lectures. So basically, I think this is going to be 4 weeks, including this week, of gravitational waves, and then there will be 3 weeks of cosmology. If you would like even more gravitational waves, much less cosmology, or vice versa, let me know. People told me that they wanted to have a little more gravitational waves, so I divided it into 4 and 3. But if you want to change it further, please let me know. Okay, thank you.
Yeah. He says that, yeah. You know, I said, why does